Hi, my name is Amelie, and I will be talking to you about the Carnot cycle and the man behind it. So this is Nicolas Carnot. He was born at the end of the 18th century, and when he was only 27 years old, he published a book, and in French it's but in English it's Reflections on the Motive Power of Fire. In this book, he wanted it to kind of be an overarching thermodynamics type book addressing questions of the time, but pertaining to his cycle, these two questions came up about heat machines. Is the work available from a heat source unbounded, meaning can we have a perpetual work produced? And can heat engines be improved by replacing steam with other working fluids? So in order to tackle this problem, he started a theoretical experiment, and the first thing he had to do was think about a heat engine and the things that would make it cause the work to be put in not equal the work out. So in effect, not have 100% efficiency. So the first thing is no friction loss, and the second is no conduction of heat between parts at different temperatures, so no loss of heat within the system. And the way that he proved this proposed cycle, theoretically again, is that he came up with a system where you have two reversible heat machines with different efficiencies. So one has a higher efficiency than the other. The first one with the lower efficiency is attached to both a cold and a hot heat sink or heat reservoir. And the second, more efficient heat machine is attached to the hotter reservoir and to the second lower one. So when you think about what's going on, you have the first lower efficiency one taking all of the heat from, from one reservoir to the next, and so you have work being pushed through there. And then the second, more efficient one is taking that and having that extra work producing more and feeding it back into the other one. And in essence, it's producing a perpetual motion machine, and that's not possible, right? We know that can't be possible. So this is how he proved that there can't be a more efficient heat machine. So here I have TS and PV diagrams, and this I'm just going to take you through kind of like the processes of the Carnot cycle on the PV diagram. So first you start at point 1 with a specific pressure and volume, and you're going to have heat added to the system. It's near a heat sink, and it's isothermally expanding. So you can kind of think of like a piston example where you have gas and exposed to heat and it's expanding. And then you get to point 2 and the heat source is taken away and you still have that gas that's expanding adiabatically. And to point 3 where now we're staying at the same temperature, but you're compressing it back to point 4, and then again you have the heat removed as you're going from there, and then once again adiabatic compression back to point 1. And you can also see this same thing kind of illustrated in the TS diagram. You have constant temperature from processes 1 to 2, and from processes 3 to 4, where 3 and 4 is the lower temperature. Okay. And here I have some more illustrations of it, kind of to give you a better visual. So like I said, it's a piston example, and point 1 is actually illustrated from the second image, and you have the gas inside the piston, like I said, and it's expanding next to a hot reservoir. And then you take the hot reservoir away, and you still have the gas expanding, increasing in volume, and then you take, then it's at a cold reservoir that absorbs the heat out of the process, and it's compressing the gas back to where it was before, and the cycle repeats itself.
427.
427. So, going back to Nicolas Carnot. Some of the reasons, I noted he was very young. He was 27 at the time, and some of the reasons he got into heat transfer is because of his father. His father was known for it, so that's for his young age. And he likened his studies to kind of the same as a water wheel, about the potential energy where you have water following and then turning into the torque of a water wheel. So that's kind of what he based it on. And he was able to come up with all of his assumptions without truly knowing the nature of heat flow. Like, that wasn't discovered yet. It wasn't until Kelvin came around and actually added the correct equations. So Carnot efficiency is equal to the hotter reservoir temperature minus the colder temperature over the hotter temperature. This relationship is specific to the Carnot efficiency because regular efficiency is basically the work in over the work out, right? So this relationship, it's pretty impressive that he was able to come up with it without actually knowing how the mechanics of heat were flowing, and he kind of just likened it to how water and potential energy were going through. So that's my time.